All right, welcome to part 3 of the single trial force plate series. Um, this is still continuing on with a single counter movement jump landing trial. We left off having having imported, processed, and filtered, and then cropped the force, acceleration, velocity, and position curves so that the first data point is where jump initiation begins. This video is now going to cover how we identify the phases of the jump. Identifying phases, as some of you may know, listeners or viewers, this is kind of a contentious subject, one that we're kind of advancing forward in the literature. So I'm going to use specific phases based on the work in my laboratory, which could be different than the ones that you want to use if you're using software already. It's likely different than what those software systems output, but this will help get the process moving of how you might extract these phases, or how you might wonder how some of these companies might be approaching this phase deconstruction method. So we've got the start, right? We already have the start of the jump. The next bit that we're going to want to find is takeoff, at least the way that I approach it. Others may go sequentially down the phases. I find that to be more complicated, and so we do them a little bit out of order so they don't happen in their temporal kind of order, but we'll first find takeoff. Now the simplest way to find takeoff is to simply go takeoff. We're going to create a takeoff variable, and then we're going to find where FZ drops down below a certain threshold. Some labs would use 10, some labs would do 20. We're going to give this a true. Now, one thing we can specify is we're going to say first. Now, that's an optional type of thing you can do, but it will tell you, okay, find when the force curve decreases below 20 the first time, right? You can type last, and it'll pull the last time. But we're going to do first, right? That would be the easiest way to do this. The only way I would recommend, or the only time I would recommend you using this method is if you have intimate knowledge of hundreds and hundreds of trials using this one piece of equipment, this one force platform, and you know that takeoff always gets pulled and always looks to be really accurate at 20 newtons, okay, or whatever, 30, 10, whatever you're using. All right, now there's more robust processes. We're going to cover a more robust process. So what we're going to use actually is I'm going to increase this threshold sensitivity, and I'm actually going to call this takeoff surrogate. Now, as we get deeper in these videos, you'll see that I'm notoriously bad at naming variables because that's a long name. And it can be annoying at times if you want to pull a variable and you got to type it out 2 words, but it just keeps everything clear for me. So what I'm going to do is find a surrogate takeoff. Okay, now this method is sort of adapted from a 2018 paper from Jason Lake and a 2020 paper from John McMahon. So we're going to, I'm sure those were kind of based on previous papers as well, but that's where I got the idea. So this is what we're going to do. I'm going to first create a surrogate takeoff. And that's going to be, I'm going to find the data point number where FZ becomes less than 30 for the first time. Now this will only work if the athletes don't unload and reduce the ground reaction force below this 30 threshold, clearly before takeoff. So if I plot an FZ that we have, so this unload that happens right here, this is problematic if this gets below 30 newtons. So I have run into this at times, so rather than kind of going through a bunch of troubleshooting ways to fix that, it's just something I'm going to have you guys think about as you work with your own trials. Now, it's kind of rare that that happens or it drops that low, but, something to be aware of. So I'm going to call this surrogate takeoff. Okay, what I'm going to do now is do a ground contact surrogate. Okay, and you can see my naming style here being kind of inconvenient, but that's okay. And we're going to find when the force curve. Now what we're going to do is not search from the first data point, but we're going to open a parenthesis and say start your search when takeoff surrogate happened. Okay, so we're going to search from takeoff surrogate to the end of the trial. And actually what we're going to do is go from takeoff surrogate plus 100, so plus 100 milliseconds. This is not necessarily something you'll have to do if you're working in a laboratory with a very precise instrument bolted to the floor. But if you're working with a portable force platform, for instance, I work with the AccuPower from AMTI, and it just sits on foot pegs. And depending on your floor surface, you may not have a perfectly flush floor. When you leave the ground, you may get a little jiggle of the force plate, even if it's very small. That jiggle is going to oscillate the signal right after surrogate takeoff. And that can be problematic, and it might try to identify ground contact much sooner than it happens. So I'm extending my search window start time by 100 milliseconds. So we'll start the search from takeoff surrogate plus 100, again, presuming that your person is in the air for longer than 100 milliseconds. I sure hope they are. Okay, so we're going to start that search, and then we're going to find when it was greater than that 30 Newton threshold. Okay, and I'm going to do true, and I want the first time this happens. But since I started my search at surrogate takeoff plus 100 right here, at the end I have to add that surrogate takeoff plus 100, right? Because otherwise, if I don't, it will give me the wrong value. It will give me the value, this number that we'll end up using, thinking that it is from start of the trial, or the first data point that we have now, rather than from the time of takeoff surrogate. Okay, so I'll run those two lines. Do I have a force curve up? No, I do not. Let's plot the FZ. Okay, and then what I'll do is just put vertical lines, again, using the v-line function I've mentioned previously. Takeoff surrogate, I'll put another v-line at ground contact surrogate. And when I open this up, you'll see it pop those v-lines in, those little red lines. And you say, well, that looks like a pretty actually good representation of takeoff and ground contact, but we're going to end up being more precise here because precision is always good. So we're not going to accept those as our real takeoff and ground contact. What we're going to do now is kind of find a residual period. We're going to find two, so bring back up the FZ plot. We're going to find kind of the center location, kind of the midpoint of flight here. Essentially, in that 2020 paper, a recent paper from John McMahon, they did the middle 50% of flight. So we're gonna try to stick to that as best we can. Sort of, right? A little bit of an adaptation we'll see here, but we're gonna get some information from here to make this takeoff more precise. So what we're gonna do here is I call this residual, and there's gonna be 2 points, a start residual and an end residual, so I'll call this residual 1. Okay. And it's going to be equal to takeoff surrogate, and then we're going to add, now I'm going to have to round this value, so MATLAB has a function called round, and just to give you an example, if I looked at weight, right, it's 1356.71, if I did round W and just left it, it will round it to the nearest whole number. If I did round W, comma 1, it will round it to 1 decimal place. Okay, so I'm going to, in here, takeoff surrogate, I'm going to add the rounded value of whatever 0.25 times the length of the time period between the surrogate takeoff and ground contacts. Right, so residual 1 is going to end up being that 25% like starting point. Okay, so 25% of rounding of 0.25 of the length, remember the number of data points, of the FZ between takeoff surrogate, separate that with a colon, to ground contact surrogate. Okay, now I've got a number of parentheses going on over here, so I'm going to have to close all those parentheses. MATLAB's good about telling you when you've closed all those. Okay? And so what that's going to be is the start of the middle portion, if I want to give this a name or a description. Start of the middle portion of the flight phase. Okay, and I will run that line. Get some space here. Now if I plot the FZ and add a V line where residual 1 was, you'll see that line is right in there, that kind of first, 25% excluded, and then we'll have that to go there. All right, the next step here is to create the second residual, the endpoint that we want to search. The whole point of this is to find the mean plus or minus 5 standard deviations of the flight phase, what the force values were there, so we can use that as a threshold for takeoff and ground contact. Okay, so that's the whole point of these residual periods. But residual 2, we're going to make this ground contact minus the surrogate ground contact minus the residual plus the takeoff surrogate. So what that's going to give us is the end point. And I'll let you visualize that here in a second. So ground contact surrogate, subtract out residual 1, add to it takeoff surrogate, and this is the end of the middle portion of flight. So I run that, and I give a V line to that graph at residual 2. Oh shoot, I got rid of the graph. Let me pull back up that FZ, and a V line at residual 1, just to get back to where we were. And then I'll add another vertical line at residual 2. We'll give it green so we can see. Hey. Oh, mistyped my parenthesis here. So you can see here, we've isolated these endpoints for this middle period. And so what we're going to end up doing is calculate the mean and 5 standard deviation of this period and end up using that as the threshold for takeoff and ground contact. The true takeoff and ground contact. Okay, so since there's errors, red here, I hate the red, get rid of it. Alright, so now, let's create real takeoff. And so this will be called takeoff, and we'll call it, the formal name so we know it's the real one. We're going to find when FZ decreases, oops, sorry, I'm missing a line here. Getting ahead of myself. What I need now is to create the threshold. So I'll call this flight threshold. Again, you notice my naming strategies are not the best. But we're going to take the mean of FZ between residual 1 and residual 2. We're going to add 5 times the standard deviation of FZ between residual 1 and residual 2. And so this is the average plus 5 SCs of flight force. Okay. Now let's make sure I've got a little, you notice this little red right here. I'm missing a parenthesis. There we go. That's one of the biggest hiccups in MATLAB is forgetting a parenthesis. Okay, and so this flight threshold, if we come over here, you'll see is using 13.9 newtons. So had you used a 30 Newton threshold or 20 Newton standard threshold, you might actually be pulling takeoff too soon and potentially influencing your variable calculations. So now what we'll do based on that flight threshold is use takeoff. And we're going to find when FZ is below or less than the flight threshold. We're going to use our true, and we're going to say the first time that happens. Okay, and so this will give true takeoff. Now this may not differ much, right? If I were to plot FZ and do a V-line at takeoff surrogate, and then do a V-line at takeoff, and let's give this a magenta color. Now these may not be too far off from each other. Let's actually do a little inspection. No, but you notice they do come out a little different. Now, one thing to think about is if I go here and I crop this x-axis to about 1000, and you look at that and you'll say, ooh, well, this new takeoff method might actually not be ideal. It may, versus just a hard 20 Newton threshold or 30 Newton threshold, it may detect it too late. Something to think about there is, are you filtering the data? In this one, I chose to filter the data. So we're going to get a little bit of effect here on the curve that is going to make that difference. If you're not filtering the data, it is very unlikely, in my opinion, that that is going to happen here. Okay? So if you are filtering the data, perhaps a hard 20 Newton, perhaps threshold would be ideal. If you are not filtering the data, you would use this current threshold we're working through now. Okay, so just something to consider. There's the paper we just put out on the effect of filtering paper on jump curves. So you don't need to filter the data, essentially, is the moral of the story, unless you really want to. But that will dictate what endpoint you do here, right? So if I were just to start over, so now in this whole script here, just to kind of, let's check this and prove this point. If I come here and I highlight those 3 lines for the filter, and I just right click and do comment, it'll put a % sign in front and void those commands. And so if I were to, let's just copy all of this. We'll start over from scratch. This is going to override everything, but it's just going to run all these lines at one time. So I'll go through here and I'll find my folder where the data are. Again, this is what we did in the first video, but this is just to check this whole filtering piece. If I plot the FZ unfiltered here, and I V-line takeoff surrogate, and I V-line takeoff real in magenta. Now you see we're right on, really close. Slight differences, but much better at determining takeoff. So again, the method that we're using here in this tutorial is probably ideal for unfiltered ground reaction force data. All right, so now we've got takeoff, let's find true ground contact. So what we're going to do is use that flight threshold and search for when that happens after takeoff. Now what I said about using portable force platforms and having perhaps a little bit of wiggle when you leave the ground and when you touch the ground can influence where, selecting ground contact too soon. So when we do this search, I'm not going to search from takeoff. I'm going to search from residual 2 because that's going to put me in the middle of the flight phase. Well, somewhere sort of in the middle, right? The last quarter of the flight phase is where it starts, and it will search from there to search for the threshold. Okay, so just kind of avoiding a potential error in when ground contact gets pulled. So let's create ground contact. We're going to use find, and we're going to find when FZ from residual 2 until the end is greater than flight threshold. We're going to say true, and we want the first time that's met. But again, remember we started the search from residual 2, not the first data point. So I have to add residual 2 to the end here. Okay. So this is true ground contact. All right, now what we'll do is, do I still have the force curve? Of course, I keep closing them. Plot FZ. And what I'll do is V-line takeoff, and then V-line ground contact. And there you have them. Using a hard and fast method to make a threshold for takeoff that's based on your trial at hand and not based on some somewhat arbitrary force threshold. Again, good for use when we're not filtering the data. Right? So let's actually just minimize this because I keep closing out of it. So now we've got those two takeoff ground contact events. We can now, and we have the start of the jump, what we can do now is identify the phase endpoints. Again, I am going to be using the phase definitions from this publication that I recently wrote in MSSE. So you might use a different set of phases. We're going to define them as they are here into 3 main phases that could be separated into 4 phases depending on what we do. And we'll go through these as we move forward. All right, so the first endpoint we're going to find is the end of the braking, eccentric braking phase, as I call it. Now, if you're using other phases, most commonly this is the exact same phase as a braking phase. In certain papers, as a stretching phase, and other papers. But we like to specify the predominant muscle action, estimated by way of whether or not the lower extremity is absorbing energy or is it producing power. So that's kind of the gist of it. So we're going to find the end of the braking phase. And so I'm going to say braking end, we're going to call it, and it's going to be equal to, we're going to use the velocity here, because this here is when the velocity crosses 0, moving in a positive slope. Right? That's what we're trying to find. So if I plot the velocity, right, so this is the velocity at the start of the jump. We go negative velocity moving downward, negative velocity slowing down, moving downward, and it crosses 0. That is when that starts to happen there, the end of the braking phase, because we've stopped slowing down and now we started moving in the other direction, speeding up. So we're going to find when velocity crosses 0 here. All right, so what we're going to do now, because sometimes if you have a preload, velocity is going to go upward. Okay, so that could be problematic, and you may think, well, maybe we need to start with a different phase. For this trial, because there was an unload, we don't have to, but you can easily reorder these phases depending on what we're working with. I'll just do a quick and like a hard and dirty kind of adjustment here in case there's trials that have a preload. So what I'm going to do is I'm going to search for where velocity, and rather than searching the entire velocity curve, I'm going to set my window, and I'm going to go set velocity from, so if we look at the graph, right, so how far does this start? And you say, well, that's actually a pretty good period of time. If you think about how long it takes to get to the braking kind of end of the eccentric braking, is at least half a second. If we think about another phase, we're going to do unloading, that can be like 0.2 seconds, 20, so depending on your sampling frequency. For us, that'd be like 200. So I can create a different starting point for where I want this search to happen. So I'll start this at like 150, so I know 150 data points or 150 milliseconds, that we are definitely moving downward. So what I'll do is search from 150 until takeoff, and I want to know when that velocity is less than 0. Okay, and we're going to say true, but I want the last time it was less than 0. Okay, that's what we're searching for. You could search for greater than 0 and search for first, but when you do it this way and you search for less than 0 and last, what that actually does is lets you get rid of this little counter that you've got to have here. So I could technically make this from 1 to takeoff, because I'm not searching for getting larger than 0, right? So that could be a useful bit of information. So you got a couple of different ways you can define that end of the braking phase. Okay, and so that's telling me at 487. So if I were to plot the FZ, so we're just going to kind of create a little basic generic plot, and I'm actually going to plot it from 1 to takeoff because we have those values now. Okay, and I'm going to hold on and y-axis right. And then I'm going to go up a couple on my keyboard and just go back to this command and now plot velocity on the y-axis to the right. So we'll have this graph, and again, we walked over this in earlier. But now what this is showing is that little curve. So now what I can do is put a V line at braking end, and you'll see it put it right there where that velocity crossed that 0. Okay, so that's that little phase endpoint. The next one we'll find is the end of the unloading phase. Now we define the unloading phase a little differently than some others. Some others call an unweighting phase, kind of just semantics for the term. But the time period for the phase, we use this time from start till the local minimum ground reaction force here, because that is actually an unloading of the body weight ground reaction force. Anytime after this, the force is increasing, so there's actually a reloading that's happening. So I think if you keep the nomenclature happening and you say unloading or unweighting, you can include periods where you are re-weighting. Okay? Conveniently, at this local minimum, the lower extremity is dominated by energy absorption and eccentric contractions, if you think about just at the gross net level. So that time point right there is kind of that onset. Here, no real muscular effort is happening. It's kind of just releasing and letting gravity pull you down, and then you eccentrically start to oppose that. So we're going to use this as an endpoint for unloading. So unload end, we're going to do another find. Now we're going to find when the force curve from 1 to takeoff, we only want to search that time period. And we're going to say is equal to, now whenever we've got an equal sign here and we're using another equal, we've got to put 2 equals. So equals equals the minimum, that's a MATLAB function, so min of the FZ curve from 1 to takeoff. Okay, now I can actually, this is probably actually a good thing that I made this mistake. We don't want to search takeoff because the minimum value will be at takeoff, right? Because our flight threshold was, what, 13 newtons? Wherever that is, 17 newtons. Okay, so we don't want to use takeoff. We actually want to use braking end right here. Because we know how the force curve here is working, right? It reduces and then it goes up through braking end. So the minimum will be pulled here. If I use takeoff, the minimum will be pulled here. We don't want to do that. Okay, so we'll do that search. I'll finish breaking these out and closing those out. Remember, we got to have the right number of parentheses. And I will put this in here. And I will add a V line for the unload end. And you see it popped in right there. So now if you were using only 3 phases, unloading, eccentric, and concentric, you'd be done with phases. Because unloading happens here. This period is dominated by eccentric actions and ends at the end of breaking. So that is technically one whole eccentric phase. And then here is concentric phase because we're dominated by concentric actions. Now there is periods of time because if you look down here and you see we've got increasing velocity, decreasing velocity. So there's actually, you can break that up into other phases based on acceleration or deceleration while moving upward, but I think that's a little bit kind of beyond the point because how much impact or how much can a jumper actually, what can they do? Can they apply into the ground during that deceleration period? I think not much. I think that because why do you decelerate is because you can no longer extend the joints. So it's not necessarily a phase that we can kind of manipulate as a jumper. It's kind of a functional limitation. Now, that may be wrong. It's just my opinion. So, you know, come at me and change my mind. My mind can be easily changed if you know me. So those are those 3 main phases. Back to our purpose. But there's another phase here that we've recently defined as eccentric yielding. Now the eccentric yielding phase is the time period where you are increasing force. So there's a positive rate of force development, but that positive rate of force development or that effort to start slowing down doesn't change your velocity at all. You're still increasing your downward velocity, so you're getting faster. So this period of time while you have a positive rate of force development and increasing negative velocity, right, that is a yielding phase or an eccentric yielding phase if we want to call it that. So we're going to end up putting a little vertical line right here separated by that minimum velocity because it's not until that velocity starts to approach 0 do you actually brake, right? So you have, if you think about it, braking initiation, that's what happens when you yield, and then eccentric braking, that's what happens when you actually slow down. So we're going to use those phases, and again, phases are controversial perhaps, but these are the ones we're going to do. And so we're going to find and we're going to search for that velocity and we're going to search for that minimum velocity. So we're going to search velocity and we're going to go from 1 to braking end. We don't need to search the entire trial, right? If we come back to the curve, we can search from here to this line here and find the minimum value there. We could find it search all the way through takeoff, but we don't need to. So we'll go 1 to braking end. And we're going to say when that's equal to the minimum velocity from 1 to braking end, we'll close our parentheses, we'll add our true. Okay, and that is the end of that eccentric yielding phase. And now if I add the V line here, for yielding end, come back to the figure, you'll see we've got that new line here. So what we have is, I'll maximize force and velocity, force on this axis, velocity on this axis. Again, we don't have labels because we're just looking. Here we've defined the unloading phase, time from start of the jump to the local minimum ground reaction force, the period of time when you actually unload your body weight. We then have eccentric yielding, where you are applying force into the ground through predominantly eccentric net muscle actions, but you are still speeding up, moving downward, so gravity is winning. Then we have the eccentric braking phase, where you are still producing force through eccentric dominant contractions, but now you are slowing that downward velocity. This phase is the concentric phase, where we are applying force for the most part and doing so through concentric actions while moving upward. So that's the same exact identical. So these 2 phases here, eccentric braking, if you think of other phases, like the 2018 paper from John McMahon and colleagues, right? They called this braking phase. It's the exact same. They called this propulsion phase. It's the exact same. The only thing is just kind of the nomenclature for how we use it or how we define them. Okay, so all we've done is separated these out. Now, if you think about that same paper, that 2018 paper from John McMahon and his team, they called the unweighting phase what we have here is unloading and eccentric yielding. So if you broke those into one phase, that would be their one unweighting phase. We've just kind of broken this down to be a little more precise, at least in my opinion. Okay, so that's for the counter movement jump phases. The landing phases, I'll just quickly run through, because some of you may want to look at landing. I know it's not very common among the sports science folks. Mostly we harp on counter movement jumping, but I think landing is just as important. So what we'll do is some landing pieces. We've already got ground contact. Okay, and so what we need now are some other phases. Now these phases are sort of incomplete. They are based on a paper that I wrote, gosh, I don't even know when, 2018 maybe. This paper, and the phases were defined here into a loading phase, which is ground contact to the peak force, and an attenuation phase, which is peak force to the end of landing, which is when you reach your minimum landing depth. This might be a little different from that. We're going to kind of update. Well, actually, we're not. I'll just stick with it to keep consistent with the literature. But it is something that we're thinking about updating. So let's define the loading phase. So this is loading end. We're going to say find when the FZ from ground contact to the end is equal to the maximum force value between ground contact and the end of the trial. We're going to give that a true, and remember we started the search from ground contact, so we have to add ground contact here to the end. Right, and so if I do this, and then if I plot the FZ as a whole, remember this is the whole thing, and then I V-line ground contact again, and then I V-line loading end, we'll see those two things here. So ground contact right here, and the end of loading right here on that peak impact force. All right, now if I were to, again, bring on the velocity, we'll need that here if we look back. So velocity again plotted on this axis. The attenuation phase tentatively will be the end of loading, so the peak force time to when we cross zero on the velocity, so about right here. Now, what I'm thinking is, and you can play around with this as you script, is that that's incorrect, because if we put that line down here on the force, you'll notice that there's a climbing in force right here before that point. So we actually hit the peak, we load, we attenuate, hit the minimum, and then we reload, perhaps like a recovery, before we actually stand up with more force and more unloading to kind of facilitate that standing up period. So again, landing phases are kind of in limbo in terms of what we should use perhaps down the road, but we're just going to simplify this that way. So we will say attenuation, well, we'll say land end, but again, this would be the end of the attenuation phase. So we're going to find when that velocity from ground contact to the end is greater than 0. Give that a true. We want the first time that happens. And again, we started our search from ground contact, so we want to specify this. So that'll give us the end of landing. And based on, if I V-line land end, you'll see that puts it in right here. And again, there's some things happening here that may change what we're talking about. And now that I think about it, we're getting kind of long in this video, but it's okay. It'll be the last thing we do. I'll actually create an endpoint here to signify that minimum ground reaction force between the peak force and the end of landing. That way we can actually say, let's actually get a little more precise rather than just talk about it. We'll actually get a loading phase, an attenuation phase, and then perhaps a recovery phase. Okay, now none of those phases, no, some of those phases are published, some of those are not, so take that with a grain of salt, but let's just do it, right, because why not? So the final phase we'll do, attenuation end, and let's find when the force curve from loading end until land end, so that's our search, is equal to the minimum of the force between loading end and land end, and we'll put our true. Now here, we need to add the loading end because that is where we started our search. All right, and let's just see what we get here. We'll run that, and then I'll add a V line for attenuation end. And yeah, there we go. So we've got our 3 landing phases here. Now we could go even further and do some things here for the standing up phase. For instance, if you're really interested in landing in time to stabilization, you'll probably want to put some phases back here. But I think you've got the idea for how you would search for those phases. So we'll end this part 3 on phase identification right there. And we'll come back later with variable extraction.